Hi, everyone. So today we're just going to do some problems on conservation of momentum to practice for your assignment. And I have three here, but I don't know if I'll get all three done. So we'll probably continue this even next week. I don't have any problems on center of mass. Center of mass problems tend to be easy, but I do want to practice some of those, and we'll do those next week as well. Okay. Well, let's start. The first problem is a 1D conservation of momentum problem, and it's kind of like the what you're going to do in the lab, which is on a linear air track. You've got two gliders coming together, and they'll collide and bounce apart. Oh, yeah, I have several of them colliding like that. I guess these are big gliders because they're like 6 kilograms, and yours are like about 100 grams, 200 grams. But let's take a look at this first question. So a 6 kilogram mass travels to the right at 4 meters per second and collides with a 5 kilogram mass traveling to the left at 5 meters per second. And in this problem, don't assume that energy is conserved. Now, I don't really need to say that, but I did say it here explicitly just to be clear about it. Energy, as we know, can be transformed into heat. And when that happens, it seems to disappear from the macroscopic level. It just appears at the microscopic level, but you don't see it at the microscopic level. That's not the way it works with with momentum. Okay, so whereas with energy, you'll see energy dissipated, and so you might not have conservation of energy in these problems. Momentum is going to be conserved. Okay, having said that, that's the initial situation. Okay, and the other thing you need to notice is that uh, uh, momentum is a vector, and so it's important to say right or left, or to indicate the direction. And in 1D, generally, we're going to just be doing left and right, okay? And so in this problem, we can take right as the positive direction, and so that'll actually be positive 4 meters per second, and left as the negative direction, so that'll actually be negative 5 meters per second. Okay, so there's the initial situation. Now, the next line, I kind of isolated it because this is kind of the point of conservation laws. You don't have to worry about the intermediate details. And there's some questions like this on the assignment too. And where things are breaking apart, and the masses are rearranging themselves. So don't worry about those intermediate details. Don't get caught up in them. So here I say a collision happens where things break apart into pieces and then stick together. In other words, they recombine. I probably didn't word that as well as I could have, but things that might break apart and then they'll recombine. And I indicate here, don't get stuck on those details. I don't have to give them to you. Don't need them. Okay, don't need them. It doesn't really matter. And afterwards, there's going to be 4 pieces. And there's going to be a 2 kilogram mass moving to the left at 10 meters per second, a 3 kilogram mass moving to the right at 3 meters per second, a 4 kilogram mass moving to the left at 2 meters per second, and then another piece. Okay, and I don't give you any of the details about that other piece. Okay, and then I've got a series of questions. Let me just quickly look in the chat, see how many people are here. Okay, good. There's some people. 4 people, it says at my end, though I can't really trust this panel. In the past it said 0 and there were definitely people present. So all right, so okay, so there's the situation. And again, like, how did you get from the 2 pieces, right, to the 4 pieces? Don't worry about it. uh, those are irrelevant details. Okay, momentum is still going to be conserved. All right, so what are the questions that I'm going to ask? Okay, so the first question is, how big is the remaining piece? Well, that's kind of obvious because, I mean, you guys have known about conservation of matter, conservation of mass, probably from high school days. So you know that that remaining piece has to be whatever size is needed so that the mass remains conserved. The only reason I add that question here is just to emphasize that you've already knew of a conservation law before you even started the class. Okay, and then the second question is, how fast is that piece moving? That you're going to use conservation of momentum to answer. What is the energy before? And I didn't say conservation of energy because energy might become heat. Okay, and so let's not assume that the energy before and the energy after are the same. And if they're not, you have 3 possibilities. Either the energy before and after are the same. I guess that's one of the possibilities. Okay, don't assume it, but it is a possibility, in which case it's an elastic collision. If the energy after is less than the energy before, it's inelastic. And if the energy after is greater than the energy before, it's superelastic. And you might say, how in the world can a superelastic collision occur? You know how an inelastic collision occur. The energy decreases because it's converted into heat by friction. But a superelastic collision, like, where did that energy come from? Well, it would also come from the microscope, but by some chemical reaction, like maybe a little bit of explosives in there or something like that. I mean, something blew apart, could have blown apart when the collision occurred, and that releases energy from the chemical level. So that's energy in the tiny little microscopic bonds, and that energy at the microscopic level then manifests itself macroscopically, and that's known as a superelastic collision. Okay, they're the rarest of the 3, but there we go. Okay, so let's answer these questions. All right, so the first question is, how big is the remaining mass? And again, I'm going to cut and paste, not to go too quickly, but it's more so I don't make errors as I'm typing. And it's kind of annoying watching me, type and make typos, and then, whoa, the usual. All right, there we go. I don't want to make typos and then watching me backspace over them, etc. So anyhow, okay, so how big is the remaining piece? So the total mass before is, you have a 6 kilogram and a 5 kilogram, so that's a total of 11 kilograms before. after you have those four pieces. One of them you don't know the size, okay? So it was a 2, a 3, and a 4, and then I just called it M4, okay? I guess this one's M1, M2, M3, M4. Actually, to stay consistent with my notation later, I'm going to call that M4 primed, just because that means after the prime means after the collision, okay? You'll see that as I go along. So what's M4 got equal to, or M4 prime got equal? Well, it's 11 minus 2 plus 3 plus 4. And so it's 2 kilograms. That remaining piece must be 2 kilograms in size. Okay, that was pretty trivial. Now, the next one. How fast is it moving? Now, to answer that, we're going to use conservation of momentum. Okay, and let me cut and paste that answer too. All right. Right there. And let me see if it disappeared on us. No, not this time. Okay. When I switch between windows, that's when it seems to go. But I'll keep an eye on it. Okay. So momentum. This is the definition of momentum right there. Okay, or total momentum. So every single mass that's moving will have a contribution to momentum, and the contribution from each one of those moving masses will be mv, okay, mass times the velocity of those masses, okay, where v is treated like as a vector, okay. Now before we have two masses, so we have to have two terms in there, and I just called them m1 v1 and m2 v2 like that, okay. So then just substituting in, I guess I'm calling m1 6 and m2 5, so m1, that's 6 kilograms, and it was moving 4 meters per second to the right. And I guess, you could draw a diagram and show the positive direction, but these problems are easy enough. I think they're easier than the kinematics problems, so you probably don't need a diagram for this. But just say, okay, if you need to, just write down right is positive, left is negative, okay? So that you're consistent throughout. As long as you don't switch the convention in the middle of the problem, you'll be fine. Okay, so 4 meters to the right, that's plus 4 there. And then M2 was 5, and it was traveling 5 meters to the left, so negative 5. And working that out, it's negative 1. And the units for momentum and MKS are kilogram meters per second, okay? So there isn't a consolidated unit like joule for energy, so it's just kilogram meters per second. You have to write it out. All right. Great. There's the momentum before. What about an expression for the momentum after? Same thing, but now you've got four masses, and it looks like that. Okay. So m1 primed, just meaning the mass one after. Okay. And multiplied by v1 primed, and so on through the four masses. Okay. And don't think that you have to even associate, m1 primed with m1 here or anything like that, because again, it really doesn't matter like how they rearrange themselves or anything like that. All right. And so let's substitute in the numbers and see what we get. Now for p primed, we could just put in the value for p. Why? That's the whole point of this. It's conservation of momentum. So p primed is negative 1. Okay. And m1 prime, 2 kilograms traveling to the left at 10 meters per second. Okay. And then, 3 kilograms multiplied by 3 meters per second to the right. Okay, that's this term here. And then 4 kilograms, 2 meters per second to the left. And then 2 kilograms multiplied by some unknown velocity, okay? And that velocity is v4 prime. And the notation there, so you understand it, it's v velocity, obviously. 4, mass number 4, primed after the collision, okay? I chose to use primes for after the collision in my notes and here, just so that we don't have too many subscripts, okay? So I just decided on a superscript rather than a subscript. Otherwise, the notation just gets overwhelming. You kind of lose track of what's going on, okay? Well, the rest of this is just, working it out. So you get negative 1 is equal to negative 19 plus 2 times v4 primed, and v4 primed turns out to be positive 9 meters per second, okay? And that positive, I've been writing in the positives explicitly, to say to the right. That tells you that the 2 kilogram piece is moving to the right at 9 meters per second, okay? So that answers the question, how fast is that fourth piece moving? All right, let's see in the chat here. Okay, we're looking good. Oh, and I lost the, Here we go. Okay, next question. What is the energy before? So the energy before is given by this expression right here. All right. And oh no, it's going to be one of these situations where this is going to happen repeatedly. All right, well, patience. Okay, so energy in this case, the total energy, is just sums of kinetic energies. There's no potential energy in these problems. So potential energy can come from lots of sources. Is there a hill here? No. Everything's on flat ground. Are there springs? No. Okay, and so there's no potential energies that you know of, and there's no electrical forces, anything like that. It's all kinetic, okay? But each mass contributes its own kinetic energy, and so you have 1/2 mv squared, but for each of the masses, all right? And so we have the first mass, 1/2 m1v1 squared, and then the second mass, 1/2 m2v2 squared. Substituting in the numbers, m1 is 6, v1 is 4 squared, okay? And then m2 is 5, and then v2 is -5. But when it comes to energy, because the velocity is squared, the negative sign drops out, okay? So -5 squared gives you the same number. It's 25, okay? So when you square a negative number, the negative sign disappears. So that's what's going on here, okay? So I dropped it out there because, just to make it easier to write down. But this works out to 110.5 joules, okay? So that's your energy before the collision. What about after the collision? After the collision, same form, but now there are 4 masses, okay? And so cut and paste here, and energy after, and there's the formula right there. Did I lose the screen? I did not, okay? So as you can see, you can see 1/2 mv squared, but for all of the pieces now. And also the primes in there, like this prime there and that prime there, because after, okay? And so substituting in, I have like a 2 kilogram piece traveling at 10 meters per second, negative, but the negative sign drops, okay? 3 kilogram at 3 meters per second, 4 kilogram at 2. That last 2 kilogram piece at 9, we worked that out already, and that turns out to be 202.5 joules, okay? So that's the answer to that one. What is the energy after the collision? All right. And then finally, is this collision elastic, inelastic, or superelastic? Well, the energy after is less than the energy before. And what does that mean? That means that, sorry, no, the other way around. Sorry, guys. The energy after is greater than the energy before, and that means it's superelastic, okay? So it's one of these situations where energy was added because of some kind of, microscopic energy being released and manifesting itself macroscopically. Okay, so there you go. Now, as I said, this is very rare. Superelastic collisions are rare. Elastic collisions at the macroscopic level are also kind of rare because there's always friction. Okay, you could have near elastic but not elastic. Most collisions at the macroscopic level are inelastic. At the microscopic level, if you ever do like particle physics or atomic physics where things are colliding, they're elastic there too because there's no place for there's nowhere for the heat to go. Okay, there's no microscopics below the microscopics. So if you're a chemistry major and you ever work on like molecular dynamics, all collisions at the molecular level are elastic. Okay, but at the macroscopic level, there's always some place where the energy can like dissipate away. Okay, it can hide itself into all these little microscopic modes of freedom, and that's why most collisions are inelastic. So like these rubber balls, like especially very very good rubber balls, you drop them and they bounce up to nearly the same height as before, but not quite as high. And they'll always bounce a little less, a little less, a little less. What's going on there is on each successive collision, they're losing a little bit of their energy to heat. Okay, so that's kind of that's kind of an example of inelastic collisions. All right, so nothing more to this problem. I just thought I'd start with something easy, but I did want to illustrate probably the most important point of this problem, which is this. Don't worry about the intermediate dynamics. Okay. All right. All right. Let's go on to the next question. Oh, actually, let me see if there's any questions in the chat here. All right, I don't see any questions. Okay, so let's go on to my next question. All right, it's this one here, and I've got it marked as hard. Okay, and you've got a problem like this on the assignment as well. Well, actually, there are two questions, but they're about the same problem on the assignment. Okay. Now, it's hard, and if you don't know the answer, or if you don't have any clue about the answer, going through all the steps is going to be very long. You'll see that in a minute. But I'll show you at the end of this problem how you can do these problems on a test or on the assignment pretty easy. Okay, or very quickly. Okay, and well, I'll tell you how. You just work backwards from the answers I give you, because it's a multiple choice test. So you have five possibilities. Okay, four of them are wrong, so you just decide which four are wrong, and the last one has to be right. Okay, and I'll show you how to do the check at the end. But if my tests were not multiple choice, and I just said just answer this question, you would see that it's kind of hard. So what is this question? This is an example where both momentum and energy is conserved. Okay, so both are being conserved. As a result, you've got two equations and two unknowns, and one of the equations is actually a quadratic, and it means you can't really avoid the quadratic. I did a version of this on the pre-recorded lecture that you watched earlier in the week. Okay. And I purposely did an easier version of that there because when I introduced the idea, I didn't want you to get caught up in all the math details and so on. We'll do that right now. But it's like a problem like that we did there. Okay. Having said that, let's read the problem and do the question. So it's the same situation where you have a 6 kilogram mass moving to the right at 4 meters per second, collides with a 5 kilogram mass moving to the left at 5 meters per second. Okay. The collision is elastic, so I'm telling you that this collision is elastic, okay? And how fast are the two masses moving afterwards? Okay, so after the collision, how fast are the two masses moving afterwards? Now, implicit in this is a different problem. Implicit, things aren't breaking apart. The two masses retain their integrity during the collision. I didn't say that, but it's kind of implied in the problem. Okay, you say, well, how do you do that? So well, it's elastic, so we're going to have conservation of momentum and conservation of energy. Both have to be conserved. So let me cut and paste this answer, and I'll go slowly because if you're writing notes, I'll make sure that uh, I'll give you time. But there are a lot of steps in here, okay? And like I said, I'll show you how to do it fairly quickly afterwards, okay? Is it all there? Yeah, it's all there. Yeah, I could see this is quite long. Okay. All right. So here's the first point. I just stated. Both momentum and energy are conserved. Let's look at momentum first because momentum is the easier of the two. Okay. So of course, when you do momentum, you've got momentum before and you've got momentum after, and you've got an expression for momentum before, and an expression for momentum after. The momentum before is given by that expression. It's no different than the previous question. Okay, and so 6 times 4 plus 5 times -5, -1. Okay, so that's your total momentum before the collision. The total momentum after the collision, there's the expression for that. Okay, and notice here I called it still M1 and M2. I didn't call it M1 primed and M2 primed. They're still the same masses. Okay, but we've got P primed is M1 V1 prime plus M2 V2 primed. Okay, and let's substitute it in numbers. Okay, so the total momentum, it's still -1 because it's conserved. Okay, M1 is 6. We don't know V1 primed. Okay, and then M2 is 5, and we don't know V2 primed. Okay, and then the rest of this is just me reducing it, reducing it. And what I did was I got to this point where I isolated V2 primed in terms of V1 primed. I could have done it the other way around as well. I could have isolated V1 primed in terms of V2 primed. But as long as you isolate one of the velocities in terms of the other, you'll be able to use it later. Why I did this, you'll see in a second, but that's what I did do. So all I did was I just isolated V2 primed in terms of V1. It's one equation. I called it equation number 1. You can't solve this, okay? Because you don't know V1 primed, so you can't get V2 primed, or vice versa, all right? You say, well, how do I solve it? Well, that's when the conservation of energy is going to have to come in. Okay, so because I'm going to be inserting this in another equation later, and the other equation is going to be quadratic, and it's going to have squares and all that. When I did it the first time, like typed it out, it looked really messy. It was hard to read. So I'm just going to do this little trick here. It's not really there's no depth to this. I'm just going to write, instead of V1 primed, I'm just going to write X and instead of v2 prime, I'm just going to write y, okay? And I'm only doing this because it just makes it so much easier to see the equations. You'll see later that when I develop the quadratic, it's got a lot of got a lot of symbols in it, so it just makes it easier. And I don't know why I called it x and y. Don't confuse this with like x and y coordinates. I just chose two variables, okay? And again, it's just because it makes it so much easier to see the equation, okay? So equation number one is basically that one right there, okay? And y there is v2 primed, and x is just another name for v1 primed, okay? All right, now what? Well, we have to develop the equation for conservation of energy. So we got the energy before, and there's the expression for it, okay? So it's 1/2 mv squared for each of the masses. And substituting in the numbers, of course, you get what we got above, because it's kind of the same initial condition as above. Okay, not kind of, it is the same initial condition as above. Okay, now after, this is different than the previous problem. The two are equal to one another. E primed and E are equal to one another because it's an elastic collision. That's what an elastic collision means. It means the energy after the collision is the same as before. Okay, so over here we have uh, uh, the energy after, an expression for the energy after is basically 1/2 mv squared for each of the pieces. But the velocities now are the after velocities. So it's v1 prime squared and v2 prime squared. Okay. Now substituting in the numbers, we know the masses and we know the energy, 110.5. We know the masses. What we don't know are the velocities there and there, like that. Okay, so we don't know those velocities. So this equation reduces down to that. Okay. Now the next thing I did was I multiplied through by 2. All right. You don't have to do this. I just did that because I don't like 110.5 and I don't like the 2.5 there. Just purely aesthetics. It makes it easier for me to manipulate the numbers later, but it works just fine. In my notes or the pre-recorded lecture, there's one point where I'm solving this problem and I multiply by through, and I multiply through by 2, and someone asked me, why did you do that? And that's why I did it here too. It's just, again, just for convenience. So you can always do the same thing to one side and to the other, okay? So it just made it a little bit easier to work with the numbers. Nothing mysterious, okay? And again, I just renamed v1 primed x and I renamed v2 primed y, okay? And then I get this equation here. So you can see here I had 110.5. That's, multiply that by 2. It's 221. The 3, that's 6. And the 2.5 twice that is 5. Okay, and you can see that I got rid of that 0.5 and that 0.5 just for convenience. Okay, and so there is my equation number 2. All right, and it's an equation in x and y, and you can't solve that one either. Okay, so conservation of momentum by itself won't give it to you. Conservation of energy by itself won't give it to you. You need both. This is kind of like when we did those problems in with Newton's laws. And the problems in Newton's laws, we had like two masses with a rope attached, and there you also got two equations, two unknowns, and you had to solve simultaneously. But there it was easy to solve it. Here it's not so easy to solve mathematically. The rest of this is just math, but like I said, it's not the easiest math. Okay, so the way you proceed is by substituting equation number 1 into equation number 2 and eliminating y. Okay, which is why I isolated v2 primed. That's why I isolated y. Okay, so right here I just wrote the two equations again so you could see them together. Okay, and so you see here, you have an expression for y, and here you have y. So taking this, let me just show you what I did here. The square brackets, that's where y is. Okay, and so that's where y is. Okay, y squared. Okay, so there's the square brackets. For the square brackets, you take this material, this expression there, and you just put it in there like that. Okay, and the next line was I don't know if I even need to show it to you, but all I did there was because I'm squaring it, I multiplied through by -1 to get rid of the signs. But you don't really need to do that because you know what, let's just get rid of that line. You don't really need to worry about that. That was just, again, one of these steps of convenience. But when we square this whole thing here, because you see the square brackets, that was the y, we square that, we have to use, what's that called? FOIL, like where you multiply the terms with themselves. But basically, you do negative zero point 0.2 times negative zero point 0.2, and that's 0.04. Okay? And then you do negative zero point 0.2 multiplied by negative 1.2 multiplied by 2 because it's the middle term, and you get 0.48x. Okay, and then finally you do negative 1.2 multiplied by negative 1.2, and that's 1.44, and that's the squared term like that. Okay, so basically I just expanded the binomial there. All right, and there we go. All right, so that's uh, that's this one here. Okay, expanded, and then I have 5 in front, so I'm going to multiply 5 times 0.04 and 5 times 0.48 and so on, and that gives me that expression. All right, and then I collected together the terms. I have a 6x squared here, and I have a 7.2x squared here, which add together to give me 13.2x squared. The other terms remain the same. Okay, and that almost looks like a quadratic, but I've got the two constant terms, and so I'm going to subtract 221 from both sides, and that gives me that there, and that is a quadratic. Okay, and so yeah, a lot of steps to get to the quadratic, and there's no way to avoid the quadratic here, so we have a quadratic. All right, and then I identify the a, b, and c coefficients. Okay, so the a coefficient is the coefficient in front of x squared. There it is there. Okay, the b coefficient is the coefficient in front of x. There it is there. And the c coefficient is the constant term there, and there it is there. Okay, so we've got those three. And at this point, you can use the quadratic formula that you know, like the minus b plus or minus b squared minus 4ac divided by 2a. All right, and I'm sure you guys have done this so many times now in life that you might as well just make use of a, a quadratic calculator. Okay, and there is one right there. Okay, this is math.com, which has a lot of nice little goodies on that site, and this one is the site, the URL for the quadratic equation solver. You don't have to memorize that URL. All you do is just Google for quadratic solve quadratic equation online, and you'll get a gazillion of these. Okay, so people have just made web pages that will solve these things. All right, so now what? Well, you get two solutions for x. Here they are. Why two solutions? Because it's a quadratic. And just like when we were doing the kinematics, we had the quadratic, we had to solve a quadratic there, we got two solutions. We had to say, well, what do these two solutions mean? Like, which one do I want? How do I interpret them? Same thing here. The first one that you get is x is equal to plus 4. Okay, now x is equal to plus 4. You go, well, what does that mean? Remember that x is just v1 primed. Okay, so the reason I did this is because could you imagine how messy that would have been if I had v1 primed everywhere instead of x? That's the only reason I did that. So x is really just v1 prime. Okay, and that means that v1 primed is equal to plus 4, but that's the original velocity. Sorry, you can't see that. Okay, that's the original velocity. All right, and so one of the solutions that you get reproduces the original velocity, which was the 6 kilogram mass moving at 4 meters per second to the right. Okay, so it's not that that solution is wrong. It's just that that's not the solution that you want because the collision didn't occur. One way you could interpret this is that instead of these two coming together and colliding and then coming apart, they come and maybe they miss one another. In which case, the 6 kilogram continues after the quote-unquote collision or near miss at the original velocity of 4 meters per second. Okay, so that's one of the solutions. That's not the one we want. We want the other solution. Okay, so because we're going to assume that there actually was a collision, the two did actually interact. Okay, and that's this number right here. I just cut and paste all the digits, and that just rounds down to negative 4.18 meters per second, and that's your v1 prime. Okay, that's the answer you want. Let's think about it for a second before we continue the problem. Does it make sense? Well, the 6 kilogram mass is moving to the right. This is the 6 kilogram mass here. It's moving to the right, and after the collision, it's moving to the left. And that's right. It was positive first, and then it becomes negative. Okay, so at least the direction is right. Okay. So there you go. We've got one of the velocities. What about the other one? What about the velocity for the 5 kilogram? And just use equation number 1. Once you get one of them, you can substitute into either one of the other two equations, 1 or 2, to get the other number. But equation number one's the easiest, so might as well use that one. Okay, so now I use equation number one to get v2 primed. V2 primed is just y, okay, to get y, which is v2 primed. And so we have that. That's equation number one. Substitute in the value of x, and you get that number, which I rounds off to that number right there. So positive 4.82. Okay, again, does that make sense? Well, the 5 kilogram mass was moving in the negative direction, was moving to the left before the collision. It makes sense that it'd be moving to the right after the collision, and it comes out positive. Okay, and so now you've got the answer. Okay, the 6 kilogram mass is going 1.8, sorry, 4.18 meters per second to the left, and the 5 kilogram is going 4.82 to the right. Okay, after the collision. All right, and that's the answer. Now, if this were a test, you say, geez, do I have to do all that work just for like a couple of points? No, and I alluded to how to do this. So we're actually going to do a check, and this is the way you could do it on the test. Okay, now, you know, there's going to be like 5 possible answers. Okay, and you might have to look at 2 of the questions. So like on the assignment, there's going to be 2 questions. I forget which numbers they are. They're 2 questions, but they refer to the same problem. Okay, and so what you do is just go through, you know, all the possibilities and see which ones work. Okay, and here, not here, but when you get the numbers and you want to say, well, did this work? Plug them into the conservation of momentum and the conservation of energy, and if they conserve both momentum and energy, then that's the solution. Okay. So let's take a look at how that works. Okay, so let's check both the momentum and energy must be conserved. All right, so if we take a look at the momentum after, that's going to equal m1 v1 prime plus m2 v2 prime. And if we substitute in the numbers that we found there like that, we get that our momentum is negative 0.98. That's a round off error. Okay, I mean, I didn't put all the digits there, but if I'd used all the digits, it turns out to be very close to -1. Okay, is that what you expected? Yeah, because the momentum before the collision was -1 kilogram per kilogram meters per second, and after the collision it's going to be the same. Okay, so momentum is conserved. That's necessary. It's necessary that momentum be conserved, but it's not sufficient. Okay, so if you find that the momentum is conserved, don't say, I found the answer. Go on and check to see if the energy is conserved, because they both have to be. And you know, probably on the test, I don't think I did this on the assignment. Probably on the test, I'm going to have one where the momentum is conserved and not the energy, one where the energy is conserved and not the momentum, and another one where they're both conserved, and that's the answer. They have to both be conserved. Okay, so let's check the energy. So there's the expression for the energy. Okay, and substituting in the numbers. All right, there we go. Now, this is the same form as above, but now instead of the +4 here, we have -4.8. And instead of the -5 here, we have a 4.82. And working that out in your calculator, it turns out to be 110.4982, which rounds off to 110.5, which is what we expected. The energy before was 110.5. The energy after has to be 110.5. Okay, so there you go. That's an example of an elastic collision. All right, and all you need are the initial conditions, and you can find all of the final conditions. I don't have to tell you anything about, you know, what's happening after. The fact that it's an elastic collision specifies both velocities. All right, let me just look at the chat here, see if there's any questions or any problems. Oh, guys look okay. And as I expected, I lost that, but that's okay. I knew that it was going to happen. All right, there we go. Last problem. Last problem here. Oh, I lost it again. How come? That time I didn't expect to lose it. Okay, so this one is a 2D problem. Okay, so the previous 2 were 1D problems. This is a 2D problem. So I say, look at the 2D diagram, and I'm going to show it to you in a second. But in that diagram, I show 2 masses colliding, and I'm going to say, assume that they collide and stick together. Okay, so 2 masses are going to collide in 2D and stick together. And the first question is, find both the x and y components of the final velocity. of the combined mass, and the other one is find the magnitude and direction of the final velocity. Well, obviously the first question is give me the answer in Cartesian, and the second one is give me the answer in polar. Okay, so let's take a look at that diagram there like that. Okay, so what you're seeing here is um, M1, and I didn't label M2, but this is M1. It's a 7 kilogram mass traveling at 4 meters per second. And this one over here, that one is M2, like that. And let me save that so I have it for later. That's M2, and M2 is 5 kilograms moving at 5 meters per second. And I forgot to put the angle in there. Let's put this angle right in here. This angle in there is 60 degrees. Okay, there we go. Let's save it again. Okay, so this is a 2D problem, and in a 2D problem you have momentum being conserved, but momentum is a vector, and so you can say that the momentum in the x direction is conserved, and independently of that the momentum in the y direction is conserved. To get the x momentum and to get the y momentum, you have to break up the velocities into their x and y components. This is just like we did when we did 2D kinematics. Okay, so remember when we did 2D kinematics and we were firing like these cannon shots, and I would say they fire at 30 degrees, and you'd have to break it up into the x and y component of the velocity. You have to do the same thing here. It's a little trickier here though. Okay, so let's start off with the looking at the 5 meters per second. This is the easiest one. Okay, let me just make sure I saved that. I did. Okay, this is the easiest one, so we're going to look at this one first. And the reason that one's easy is because that velocity is purely along the x direction. So there is no y component to it at all. Okay, so Vx is going to be 5 meters per second. Vy for that one is going to be 0. All right. The other one is the one that's more interesting because that 4 meters per second is not along the x or y direction. It's at some angle. Okay. Now, what's tricky about this is that, when we were doing the 2D kinematic problems, usually, I put the origin right at the tail of the vector and then it was resolvable. But here, it's not the origin, the tail of the vector is not at the origin. Rather, it's the head of the vector that's at the origin. You go, well, how do I resolve this? Like, how do I do the sine and cosine? And, you might be tempted to say, oh, I'm just going to do 60, and that's not quite right, okay? So let's take a look at how that geometry works out, okay? So my next diagram over here, all right? And what I have here is just the 5 meters per second, or I'm sorry, lost track now. That was this one. Sorry, 4 meters per second. Okay. So over here, this is the 4 meter per second vector. Okay, and you'll see that it's coming into the x-axis at 60 degrees like that, and you go, well, I need to calculate, this. I need to calculate. Let's do this in red, I guess. This is v1 x, and that's going to equal something cosine something, right? And then I need to do v1y, and that's going to equal something sine something. Okay, and you say, well, what do I put here? Well, the magnitude, that's easy. That's the 4 meters per second. Okay, that's just how fast is this thing going, irrespective of direction. And so this is 4 there like that, and there it's 4 there like that. But the question is, what angle do you put in there? You might be tempted to just say 60, but that's not right. Okay, you might even be tempted to use this angle in here, okay, which would be 120, and that would be also wrong. And you say, well, how do I do it then? So to resolve a vector, you really want to resolve it off of the tail. But the tail is not at the origin, so what you do is you put a little temporary origin right at the tail there like that. Okay, so this is plus x, and that's plus y there like that. Okay, so I hope you can see what I did. I mean, like wherever the tail of that vector is, that's where you're going to put a little temporary origin. Okay, and now you measure the angle. And now the way I taught you to measure the angle was to say, okay, start from here and go all the way around counterclockwise, 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 counterclockwise like that. Okay? And that would mean it's 360 minus whatever this angle is. And this angle in here turns out to be 60 degrees. You go, well, how do you know that it's 60 degrees? Well, let me see if I can do this in a different color. So this x-axis here, and that x-axis there, those two x-axes are parallel to one another. And whenever you have a line, the blue line there, cutting across two parallel axes, this angle here equals that angle there. Okay. Now this is one of the Euclidean postulates. I forget which one it is, and it's been so many years since I've done Euclidean geometry, I don't remember. But it basically comes out of Euclidean geometry, which is usually taught in like grade 10 or 11. Okay. So, well, if this is 60, well then this angle here must be 300. Okay. And this would definitely work to put 300 in there. Okay. However, I'm going to show you a slightly different way of thinking about this. If you measure counterclockwise, that's positive. Well, what do you think if you measure it clockwise? That's going to be negative. So the angle that you put in here can either be 300 or it could be negative 60 degrees. Okay? Like that. Now, you say, but I really want to stick to the 300. That's what I'm used to. Yeah, get used to this other way of doing it, because our next topic is going to be rotational motion, and you're going to see a lot of clockwise, counterclockwise things there. So just think about it this way. You know, the way I taught you to do this before is just measure counterclockwise, positive counterclockwise. Add something more. If you want to measure clockwise, or you have to measure clockwise, that's negative. Okay, so counterclockwise positive, clockwise negative. All right, and so this is going to be negative 60, and this one turns out to be also negative 60, like that. All right, it doesn't make any difference for the cosine. For the cosine, whether it's positive 60 or negative 60, it's the same number, but it definitely makes a difference for the sine. The sine is an odd function, which means if you take the sine of negative 60, that's the negative of the sine of 60. Okay, and so there you go. That's how you work out those guys there. Okay, so this angle here, don't just use it blindly. Realize that that angle has to be used to obtain this angle, and it's actually the same in value. It's just the opposite in it's just the negative of the angle. Okay, now you got to watch it, because I mean there's other possible geometries that I can look at, so you probably have to reanalyze it each time depending on what's going on. And reanalyzing it means what? Going to the tail of the vector, wherever that is, and putting a little temporary origin there with an x and y axis, and then measuring the angle like that. Okay, don't do that off of the head. That would be wrong. You go to the tail and you look at the tail, and you add a little coordinate system at the tail to get the angle. Okay, so I hope that's clear, because that's you know, if there's anything hard about this problem, I think this is it right here. Okay, but once you've got that solidly in your mind, you'll be okay. All right, let's switch back here, and let me cut and paste this answer. It's not that long, but cut and paste it. All right, and how much time do I have? Oh, we'll finish in time. Okay, so did I lose it? No, I didn't. Good, didn't lose the screen. Okay, so for the 7 kilogram mass, we have, we call that one M1. Okay, so that's M1. And so we have V1x and V1y. V1x, well, that's that cosine, 4 cosine negative 60 degrees. We just reasoned out why that's the case. That turns out to be 2 meters per second. Okay, and V1y, that's 4 sine of negative 60 degrees. That's negative 3.4641 meters per second. Okay, so there you go. There's the V1 broken up into its x and y components. For M2, that one was the easy one because it was purely along the x direction. Okay, and so it was 5 meters per second along the x direction. So V2x is 5 meters per second. V2y is 0. There's no y component at all. Okay, so there you go. We've broken up the all the velocities into their x and y components, and you say, well, now what? Well, now we calculate the total momentum before, and that's this here. Okay, both of these expressions are the total momentum before. Okay, notice there's no prime in them. So you say, well, why are there two expressions? Because momentum is a vector, and this is the x component, and that's the y component. All right. Now the total mass. Oh, sorry, not yet. Okay, so px, that's going to be m1 v1 x plus m2 v2 x. Okay, so same expression as above, m1 v1 plus m2 v2, but only the x components. We'll give you the x component there. Okay, and then it's easy to substitute in. M1 is 7, V1x, we found it up here. V1x is 2, M2 is 5, and V2x is 5. Okay, there it is there. Turns out to be 39 kilogram meters per second. Okay, the y component of the velocity is m1 v1 y plus m2 v2 y. Okay, and again, mass 1 is 7, and there's v1 y from here, and then mass 2 is 5, and there's v2 y from there. It's 0, and that gives you that number there, negative 24.2487 kilogram meters per second. That's the total momentum before, okay, as a vector. There's its x component, there's its y component. Great. What about after? Well, after there's only one mass. Now, I didn't draw that in the diagram, okay, but if we go back to the diagram very quickly here, whoops, that's not how you do it. That's this, and that's not the diagram we want. We want this one. Okay, so when the two collide and come together, they stick together, they're going to head off, and I think your intuition's would tell you that it's going to go off in that direction like that. So it's just one vector because there's only one mass afterwards. Okay, and that mass, how big is it? Well, it's the combined mass, so it's the 7 plus 5, and that's 12 kilograms. Okay, so the 7 and 5 collide together to give you a lump of 12 kilograms. Okay, and now the total momentum before is just, there's only one mass to contribute, so there's just one mv. Okay, so px primed is going to be mvx primed. Okay, and that's got to equal 39. So this is equal to 39. That m is going to be 12, and vx primed, well, we can solve for that. Okay, so 39 is equal to 12 times vx primed, and that gives us that vx primed is 3.25. Okay, same thing for the y component. Okay, so the y component of the momentum after the collision, all right, there's only one contributor, so there's just one mv here, mv, and m, I'm using capital M for the combined mass, multiplied by vy primed. M is 12, and vy primed is unknown. Okay, and the total momentum y component after, that's the same as before up here. Well, you can't see that. Let me scroll it down like that. Okay, so that total momentum y component after, that's the same right here. Okay, and then solving for vy primed, we get that number. Okay, and is that in quadrant 4? Because if you go back to the diagram very quickly, you see the green vector. Intuitively, it makes sense that that vector is going to be heading into quadrant 4, and in quadrant 4 you expect x to be positive, it is, and y to be negative, it is. Okay, so there you go. That answers the first question. What is the x and y component of the velocity of the combined masses after the collision? And there it is. Okay, now what about the converting it to polar? Okay, so that's the Cartesian answer, and the second question was give it to me in polar. And polar, it's a magnitude and an angle. Okay, so for the magnitude, it's the Pythagorean theorem. It's the square root of the x component squared plus the y component squared, like that. So the x component squared, then add the y component squared, then take the square root of all that, and we get 3.82. Okay, so this mass is going to be moving at 3.82 meters per second. All right, after the collision. What about the angle? Well, the angle is going to equal the inverse tangent of the y component divided by the x component. Okay, so remember that from when we did vectors. All right, so there's the y component divided by the x component, and I should, I guess, say here plus 360 degrees, y plus 360. Why did I do that? Because it's in quadrant 4. Okay, and that's going to give us a negative 31.9 degrees plus 360. And here again, we can use this trick where, I don't know if it's a trick, but this interpretation, where either we can go ahead and add in the 360, and we get some positive number there, like a little less than 300, okay? And that's if you're measuring counterclockwise. But you know what? Adding that 360 is actually optional. Okay, now I didn't say that when I first introduced the vectors, because and the conversion between polar and Cartesian, because I didn't want to overwhelm you at that time. But now we can see that, you know what, you could just stick to that negative 31.9, and that is the correct answer. That is the correct answer. Only because it's negative, you have to think about measuring it clockwise. Okay? Now, in quadrants 2 and 3, that isn't this problem, but if you're in quadrant 2 and 3, if this vector had been in quadrant 2 and 3, you have to add 180. You can't avoid that. That absolutely have to add 180, otherwise you get the wrong answer. But here in quadrant 4, adding that 360 is optional. And you say, well, what's the option? Like, what's the difference between the two choices? Well, it's whether you want to measure clockwise or counterclockwise. Okay, so let's go back to the diagram for a second here. Okay, so it was negative 31.9. Okay, so that's like going this way. So because it's negative, we're measuring clockwise here like that, and it's negative 31.9. Okay, you say, but I really want to add that 360 in there. Yeah, well then you would be measuring this angle here like that. Okay, so whether you do it one way or the other way, it doesn't matter. But let's start getting used to this idea of a negative angle as meaning you still start from the positive x-axis. Okay, so you still start from here. Okay, but if it's positive, you go counterclockwise, negative, you go clockwise. All right, so that answers that question. And that ends the lecture. A little bit more than I wanted to go, but how's that, everyone? Is that okay? Any questions before we just end the live stream? If so, we're done. So I'll just wait a second here to see if there's any, because of the lag, the 30-second lag between when I speak and when you hear me at your end. I'm not seeing any questions. So shall we call it a day? All right. Okay. Bye-bye. Bye-bye, everyone. I'm going to end the stream then.